Okay, we've got trig integrals today. Section 8.3a, and we're out of the Larson book. And the types of trig integrals that we're going to deal with today are going to be ones that involve sine or cosine. So I'm really just going to be practicing a whole bunch of problems today and seeing how we can integrate these. So sine cubed x cosine to the fourth x dx. First thing we're going to look for is something to substitute. Some of you guys might be thinking, alright, should u equal to sine x, or should maybe u equal to cosine x? Or maybe it doesn't matter. Okay, but in this case, because there are an odd number of signs, because we notice we have sine cubed x, we're going to separate one of those out so that that odd man out of the sign will become part of our du. So what we'll do here is we'll rewrite this so it looks like sine squared x cosine to the fourth x, and then the other sine x dx sits on its own. So anytime you have one of them being odd and one of them being even numbered of sines or cosines, separate one of those out. So in order to have sine x dx be our du part, then that means we should let u equal to cosine x, so du equals to negative sine x dx. So using our substitution, what do we end up having over here? We will also have to use the Pythagorean identity, so that means using sine squared x plus cosine squared x equals to 1, because since my u is a cosine x, you should be able to tell that right here we have u to the fourth power du, but I have this extra sine squared x sitting over here by itself. So we're going to have to let sine squared x be replaced by 1 minus cosine squared x, which is going to be 1 minus u squared. Now we have a nice little polynomial function to integrate. This is going to be u to the fourth minus u to the sixth du, which is 1/5 u to the fifth minus 1/7 u to the seventh plus c. We have negative 1/5 cosine to the fifth x minus a negative, so that's plus 1/7 cosine to the seventh x plus c. How about if we have a cosine cubed x over square root of sine x dx? So this is similar to example 1 in that we have an odd number of cosines in this case, but we also have a square root here. Again, you need to think about what we want to substitute. Your choices are usually either going to be, in this case, u equals to sine x or u equals to cosine x, but which one do we want? Now, u equals to cosine x would be a poor choice. Why? Why do I say that? Because the derivative of that will give us a negative sine x dx, and look where our sine is. Not only is it in our denominator, but it's got a square root over it. So we don't want to use that. So we're going to break off a single cosine and separate that. So we're going to have ourselves cosine squared times cosine x dx over the square root of sine x. And we're going to choose u to equal sine x, so du equals to cosine x dx. So you really need to think about what you want your du to be, not only what your u is, but consider what the du is. So in this case, we're going to leave ourselves with a cosine squared x up here in our numerator. So that's going to be 1 minus u squared from our Pythagorean identity. Cosine x dx is our du, and square root of sine x will be square root of u. So rewriting this, I have 1 over square root of u minus u to the 3/2 power du. So some of you guys may want to write this 1 over square root of u as u to the negative 1/2 power. And we can just do our power rule and integrate this. Add 1 to our exponent, so that becomes u to the 1/2. Multiply by the reciprocal. And same thing with the second part. U to the 5/2 and multiply by 2/5, and then our plus c. Then we'll back substitute, so we have 2 u to the 1/2, so that's square root of sine x minus 2/5, and then I can still write this actually as the square root of sine to the 5th x plus c. Alright, example 3. What about cosine to the 4th x dx? So, just cosines in there. Can I do the power rule? Is this going to be 1/5 cosine to the 5th x plus c? Think about that. Looks good, right? Problem is the chain rule. We don't have a sign in there. So we need to be a little creative. We need to do something different. We are going to have to use the power reducing formula here. Now, previously in our u substitution section, we integrated a cosine squared. So I need to think of this as a cosine squared x quantity squared dx. Now the power reducing formula, I don't know if you guys remember, but it comes from the double angle formula for cosines. I did this with you guys once before. Cosine of 2x equals 2. Remember, this is cosine squared minus sine squared. And then instead we think of this as 2 cosine squared x minus 1. And there's also the 1 minus 2 sine squared x, but that's not the one we're going to want to use today. We're going to use this one. So if you solve for cosine squared x, we get 1 plus cosine 2x all over 2. This is called the power reducing formula. I'm not going to give that to you guys, and I'm not going to give you a hint and tell you, okay, don't forget, if you see something like cosine to the 4th x dx, make sure you use the power reducing formula. You need to remember this. So what's going to happen is we're going to plug that in here. 1/2 times 1 plus cosine 2x quantity squared dx. So I'm going to take this 1/2 squared and put it out in the front to be a 1/4. Then I'll get 1 plus 2 cosine 2x plus cosine squared 2x dx, which pretty much looks good. We can integrate the 1, we can integrate the 2 cosine 2x, but how do we integrate the cosine squared 2x? Well, guess what? You're going to have to use the power reducing formula one more time. What you do need to be careful here now is when you do the power reducing formula one more time, that you notice that your angle is now 2x. So let's work this out and be careful when we write it. Okay, so working on this next line, I'm going to substitute in my cosine squared 2x with the power reducing formula. That leaves me with a 1/2 and then 1 plus cosine 4x dx. So now I'll integrate. Integral of 1 is an x. Integral of 2 cosine 2x is sine 2x. I have a 1/2 here. My integral of 1 is x. Integral of cosine 4x is 1/4 sine 4x, and then plus c. Now I'm going to combine my like terms. I've got an x here, and x is over here. Okay, so here I have 1/4 x plus 1/4 times a 1/2 x, so that's 1/8 x, plus 1/4 sine 2x, plus 1/4 times 1/8, so 1/32 sine 4x plus c. I'm just going to put these two things together and then write out my final answer. So this can get a little bit tricky. Hopefully you write really neatly so that you keep everything straight. And then our last example. Integral of 16 sine to the 4th x cosine to the 4th x dx. So this one's a little different now. The ones that we did earlier, the first two examples, we had an odd number of sines or cosines, and that was easy to break off. But now we have even numbers of sines and cosines. I need you to think outside the box a little bit here. What can we do here? What do you guys see? Well, you could think of this as 2 sine x cosine x all to the 4th power, right? Because 16 is 2 to the 4th, and all of these are raised to the 4th power as well. And you recognize 2 sine x cosine x? Some of you guys may. That is sine 2x all to the 4th power. So this is now kind of like the previous example where I had cosine to the 4th x. I have a sine to the 4th, but now it's a sine 2x. So we are actually going to do something similar to the last one, but we're going to use the power reducing formula for sines. So that was the one where it says cosine 2x equals to 1 minus 2 sine squared x. So solving for sine squared x, we have 1 minus cosine 2x all over 2. But notice that we have an x, and over here we have a 2x. So it's going to change a little bit. Our sine of 2x can be replaced by 1 minus cosine 4x all over 2. And that's going to be quantity squared because this is to the 4th power. So I actually need to FOIL this out. I'm going to square my 1/2 and write it out in the front. Then I'll have 1 minus 2 cosine 4x plus cosine squared 4x dx. We can integrate the 1, we can integrate the 2 cosine 4x, but guess what? We need to power reduce cosine squared 4x one more time. So let's be careful when we do that part. Okay, so from the previous problem, cosine squared x is 1 plus cosine 2x over 2. So in this case, I'm going to have 1 plus cosine, now we have to double the 4x, so it becomes 8x all over 2. And then dx. Now we integrate. So I get x minus 1/2 sine 4x plus 1/2 x plus 1/16 sine 8x plus c. Combining our like terms and distributing our 1/4, we're going to end up with x plus 1/2 x will be 3/2, so I end up with 3/8 x minus 1/8 sine 4x plus 1/64 sine 8x plus our constant c. That was a long one.